We are now ready to define the incremental method. The incremental method has three steps. The first step of the method, as we saw just now, is to operate at some DC offset or bias point VDID. Okay, so you have to boost your signal in a way that the circuit operates at some DC bias. Okay, so let's call that VDID as an example for the circuit that we've been using. As a second step, what you do is that you superimpose a small input signal VD. Okay, this is the signal of interest. This signal is superimposed on top of your DC offset VD. Then as a third step in your incremental method is the recognition that the response ID to the small signal VD is approximately linear. Okay, so if you boost your signal up by VD ID, capital VD, capital ID, and you superimpose a small signal on top of that, then your small signal response, small I, small d, to the small signal input, small v, small d, will be approximately linear. So this is the basic method. So before I move on to looking at some of the mathematical foundations of it, I'd like to formalize some notation that I have very quietly snuck by you. Okay, so notation. Okay, this notation is the following. My total signal is ID, and that is going to be a sum of a DC offset plus a small signal response ID, where in this case, ID is my DC offset. And ID, small d, is a small superimposed signal. All right. And then by adding up the DC offset and the small superimposed signal, I get my total variable or my total signal. Okay, now this is true whether it's for the input or whether it's for other measured quantities in the circuit. So given this nomenclature and given the small signal method, before we actually go about building circuits, I would like to spend a little bit of time looking at what does this really mean mathematically. Okay, I've shown you this thing graphically and shown you why graphically this looks like it must be true because a small region of this curve looked linear. And then I showed you a small signal circuit and showed you how we can construct the small signal model. As a next step, I'd like to show you some insight as to why the small signal response is actually going to be linear. Okay, I'd like to do some math and demonstrate to you that there's some mathematical foundations to the small signal method. So what did we do so far? So we took our signal, which was ID, was some function of the input VD. Okay, notice that this was nonlinear. Then what we did, let's just walk through a construction and look at what we did, and then I'll convince you why that should yield in a linear response. So what we did was we replaced ID with something, replaced VD with something else. Okay, so I have an input VD here. We replaced VD as follows. We took VD and we said, I'm going to replace it with a DC value plus a small signal, a very small signal value. Okay, so this was my large DC value. And because I'm doing math here, in math, we represent small values or small changes about a DC value using a delta notation. So let me just call that VD. Okay, small v, capital D, and delta VD. Okay, so delta VD represents a change, a delta about the DC offset VD. So this is a small increment or a small change about VD. Okay, when we talk about circuits and so on, notice that we are going to replace this more conveniently with small v, small d. All right. So just when doing the math, I'm going to use delta VD, but in circuits, we'll use a more convenient notation, small v, small d. Okay, so what we really did was we took our input, VD, and noticed that the signal, the output of interest was ID, which was some nonlinear function of VD. So what we did was we replaced VD by a sum of a DC value and a small signal, okay, a small increment about that DC value. Now, you go back to your math. Okay, when you see signals that are a constant value and you're looking to observe changes about that small value, what mathematical technique comes to mind? Well, Taylor's series comes to mind, and I'm going to use Taylor's expansion to expand f of VD about the point capital VD. Okay, so I'm trying to figure out how the function behaves for a VD for a small increment about some DC value VD. Okay, so Taylor series is a natural mathematical tool to use in this situation to look at what my small signal response or small incremental response is going to be about the point capital B capital D. So let's write out Taylor series for this situation where I have ID equals f of VD and where I replace VD with capital V capital D plus delta VD. Okay, so let's go ahead and write that out. So this is my ID. So what is ID by using Taylor's expansion? Well, ID is simply going to be f of the function at that point, the DC point. Okay, so it's a function at the DC point plus some change. Okay, so f of vd is simply the function computed at the DC point plus some change. That change is given by the rest of this expression. So that change is given by the derivative of the function about the point vd times the change plus other stuff. So the derivative of the function about that point is given by this. So d by dvd of the function. So the derivative with respect to vd of the function f of vd, and that would have to be evaluated at the point vd equals capital Vd times the increment, okay, plus other stuff. Okay, so it's by Taylor series, I compute the function at the fixed point, okay, at the DC point, and then I take the derivative, the first derivative of the function, df of vd by d by dvd of f of vd, the first derivative, evaluated at vd equals capital Vd, times the incremental change in Vd. Okay, plus I take the second derivative, so it's plus 1 by 2 factorial of the second derivative of the function. So it's second derivative of the function. Okay, and that evaluated at the same point, Vd equals capital Vd, and that times delta Vd whole squared. Okay, and that plus other terms. Okay, so what do I have so far? So ID can be expressed as the function evaluated at the fixed point plus a component related to the derivative of the function at the point Vd equals capital Vd times the incremental change plus 1 by 2 factorial times the second derivative times the square of the change, and so on and so forth. And those are higher order terms. Okay, so let's state this for a second. To simplify my life here, what I'm going to do is notice that I chose delta VD to be small. Okay, so delta VD is small. Okay, if delta VD is small, then what I can do is I can neglect higher order terms. Okay, so I'm going to neglect higher order terms. I'm going to neglect higher order terms because delta VD is small. Okay, because delta VD is small, I'm going to neglect higher order terms. So I'm going to neglect the term related to delta VD squared. There's a term related to delta VD cubed and the fourth order and so on and so forth. Okay, I'm just going to focus on the fixed term and the term related to delta VD.